Stereochemistry. It is the study of three-dimensional structure of molecules, and it deals with the spatial arrangement of atoms and the groups in a molecule. So there is a term stereoisomerism. So stereoisomerism is shown by the isomers having the same structure, but they differ in their spatial arrangement, that is having the different configuration. Now see, there is a term configuration and the I think configuration and some other term is there. I will take this afterwards. What is the difference between it? See, there are the different configurations are possible because carbon forms mainly the covalent bonds, and these have the directions in the space. Okay, so molecule it is a 3D. So there are two types of stereoisomerisms. The one is optical isomerism and the second one is geometrical isomerism. So see, stereoisomers, they are mainly are of two types: optical isomerisms and the geometric isomers. Now see, optical isomerism is shown by only those structures which are not superimposable on their mirror images. Not superimposable on their mirror images. And such structures do not have any element of symmetry and are called asymmetric structures. Now see, we are going to see the element of symmetry. So optical isomerism, in that here is a enantiomers. So enantiomers, they are the mirror images, superimposable mirror images, optical isomers. So in that comes enantiomers. There are LIGO and the dextro. L stands for, this is the lactic acid, example of lactic acid. So there is a LIGO, okay, and there is a dextro. L stands for LIGO, D stands for dextro. That depends on the this molecule rotates the plane of polarized light to the left or right. So if rotates the plane polarized light to the left, then it comes little LIGO, and if it is rotates to the right, then it is dextro. So right now you have this in this stereoisomerism, you have the term stereoisomers. These are of two types, geometric and the optical isomers. So optical isomers shown by the structures which are not superimposable on their mirror images. And see, it is and it is based on the tetrahedral geometry of carbon. See, if it is a regular tetrahedron carbon, okay, which is attached to the four different groups, then all the element of symmetry disappears. Means the carbon atom at the center of the tetrahedron, okay, to which the four different groups So students, there are the connection problem, right? So it is getting disconnected in between. Yes. So the carbon, okay, at the center of the carbon to which the four different groups are attached. The carbon to which the four different groups are attached. So that carbon, we called it as a chiral carbon or a asymmetric carbon. So the presence of chiral center in the molecule leads to the molecular chirality. See here, stereoisomerism basically are of two types. Okay, so first is optical isomers, and the second one is geometric isomers. Stereoisomers. So geometric isomers, in that examples like cis isomer is there and a trans isomer is there. You see, geometric isomers, they are differ in their geometry, and optical isomers, in that comes the example that is enantiomers. Now see what is a molecular chirality. So when a molecule contains the carbon, if that carbon is attached to four different atoms or groups, the carbon to which the four different atoms or groups are bonded is called the asymmetric or a chiral center. So the presence of this chiral center in the molecule leads to the molecular chirality. Means when we see the molecule has the chiral center, when the carbon present in it, it is attached to four different groups. So the chirality of a molecule can be determined by finding whether the molecule is superimposable on its mirror image or not. Now see, here is an example. In this molecule, see this red dot, this is the carbon. Okay. So here this carbon is a chiral carbon. So why? Because see, on the left side it is attached to the double bond of H is there. Here it is attached to OH. Then here it is H, and on the right hand side this part is there. So this carbon is attached to four different groups. So in this molecule, this is the one chiral center. Then the next carbon you see here, blue dot. So this is on this side, it is attached to this carbon having the OH and this aldehyde group. Then uh, attached to this hydroxyl group. Then here it is H. Okay, and on the right hand side it is attached to CH2OH group. So this molecule contains two chiral centers. You can see. Okay. So this red dot is there, that is the first carbon, and the second one is the blue dot, this carbon. Now see, here is the example. this carbon. Now these are the enantiomers. So enantiomers, these are the mirror images. So this carbon attached to four different groups, 1, 2, 3, and 4. It is shown. And there is a wedge line and there is a dotted line is there. So this is the S enantiomer and this is the R. So there is a, so this S and R, it depends on these groups. Okay, like when we have to decide it, so we don't have actually naming of this S and R in this. So that S and the R structure, okay, in enantiomers, it will depends on the priority of these groups. Means we see the different groups attached to this carbon, and accordingly we numbered it as 1, 2, 3, 4. So if it is clockwise, then we see as a, we name it as a R enantiomer, and if it is anti-clockwise, then it is S enantiomer. So this is the structure. Enantiomers are the mirror images, superimposable mirror images. Molecular chirality it depends on the presence of the chiral center in the molecule. See, now if the molecule and its mirror image are non-superimposable, then the molecule is chiral or a disymmetry. All the atoms and the bonds in the molecule and its mirror image superimpose on each other, then the molecule is chiral. So see here, example is there. This is the tartaric acid. So see in the tartaric acid, these the numbers shown 2 and 3. Okay, these 2 and 3. These are the chiral centers. Okay, and why it is a mesotartaric acid? Because if we take a plane 2 and 3, if we draw a line, okay, between these 2 and 3, then the upper part, this above part and this below part is same. If we put a mirror in between this 2 and 3, there is a plane of symmetry. So this part and this part is the same. What is the element of symmetry? So there are plane of symmetry is there, center of symmetry, and also the axis of symmetry, center of symmetry or axis of symmetry. So if plane of symmetry, center of symmetry or axis of symmetry is present in the molecule, then we call that molecule is a chiral or a symmetrical. You see the previous example, this mesotartaric acid, okay, there is a plane of symmetry is present. So see if the molecule and its mirror image are not superimposable, then the molecule is chiral or disymmetric. So see there are different types of element of symmetry. there is a plane of symmetry, center of symmetry, or an axis of symmetry. So if any one of these is present in the molecule, then we call that molecule is a chiral or a symmetrical. And if all the elements of symmetry are absent, then the molecule will be a chiral and hence it exists in optically active forms. If all the elements of symmetry are absent, then the molecule will be chiral, okay, will be chiral, and hence it will exist in optically active forms. So we are going to see now what is the plane of symmetry. See, plane of symmetry. If we take the example, this tartaric acid, so it is a mesoform. That is, plane of symmetry is present. So what is the plane of symmetry? The plane of symmetry, see here, it is an imaginary plane that passes through a molecule such that atoms or groups on one side of plane form a mirror image of those on the other side. Here is the example, tartaric acid. So here if we put a mirror, okay, then this part is it will become mirror image of this. One side of plane forms a mirror images of those on the other side. So the plane of symmetry may pass through atoms, between atoms, or both. So it is the imaginary plane that passes through a molecule such that atoms or groups on one side of plane form a mirror images of those on the other. So see here another example is there. So this is a cyclic ring. We have the bromine and the bromine substituents. So here it is this. They are on the same side of the plane. So if we put a line here, okay, imaginary line here, then this part will become the mirror images of this part. So there is a plane of symmetry is present. And now see this example. In this bromine is on this side of plane, and this is below, and this is the above the plane. Okay. Then if we put a mirror image, imaginary plane here, okay, if we put this, so this will not become the mirror images of this part. So here the plane of symmetry is absent. So here is the example, tartaric acid. We called it as a mesoform. Okay, and plane of symmetry is present in this example. So this molecule we can say it is a chiral. Symmetry is present here, plane of symmetry. And the next one is the chiral, because no plane of symmetry is present. Next one is center of symmetry. The center of symmetry here is the example. So see the substituents, CH3. This carbon has the substituent CH3 and H. Then this carbon H and the COH. Here this carbon has the substituent H, this above, and the CH3. Okay, and here it is COH and H. This is center of symmetry. It is a point. So here you can see this point. So it is a point in a molecule from which lines drawn on one side and then produce two equal distance on the opposite side meet exactly the similar points in the molecule. What here it is the point. Okay, so here is a dotted line. So if we draw a line from here to here, okay, here is a COH group, and the same from here in the opposite direction, we are drawn the line. Okay, then here is the same group COH. Also for this, if we extend this line, then here it is H, and also extend here from here, okay, H, and see this one CH3 is present on this side, and if extend this line here, the same group is present CH3. So here it is this point, okay, it's the center of symmetry. So see, this phase can be applied only to three-dimensional structures, particularly to organic molecules which have the ring system. Here, this is the example of 2,4-dimethyl cyclobutane 1,3-dicarboxylic acid. So see, this carbon, you see here, these carbons, okay, these four carbons are the asymmetric carbons because they are attached to four different groups. So, though they have these four asymmetric carbons, we say that this molecule is optically inactive. Why? Because the presence of this center of symmetry, okay, center of symmetry is present in this molecule. So, we call it as the molecule is achiral. Next one is the alternating axis of symmetry. So see here is the example is given, alternating axis of symmetry. So it is the line. What is the alternating axis of symmetry? It is the line passing through the molecular structure around which if we rotate it through an angle of x, okay, so x, it can be a 180 degree or 90 degree, okay, followed by reflection on a mirror placed at the right angle to the axis, produce the same phase of the molecule. So see here, example is there. This example here, it contains four asymmetric carbon atoms. So see, here it is the line passing through the molecular structure. Okay. So if we rotated this molecule in 180 degree, so see the substituent here. The first, this carbon has the phenyl ring here and the hydrogen atom. Okay. So here we rotated this molecule 180 degree around this S2. Okay, this is the line passing through the molecular structure. So we around rotated this by 180 degree. Then after the rotation of this molecule by 180 degree, see the substituents present. And then we place the mirror here. We rotated this molecule by 180 degree, and then we place mirror here and see this this molecule and this molecule. Okay. See the substituents, the position of the substituents. They are the same above and below. See, this is the alternating axis of symmetry. What? This is the line. This line passing through the molecular structure, okay, around which he rotated this molecule in a 180-degree, and then it is reflected on a mirror, okay, placed at a right angle. Okay, this line is perpendicular to the mirror. Then it produces the same phase of the molecule. So it is this substituents and C, the substituents here on the carbon atom, they are the same. It is called the alternating axis of symmetry. See, if the molecule contains any one of these symmetry, like plane of symmetry, if there is a center of symmetry, or there is an alternating axis of symmetry, then that the molecule is optically inactive.